go. I was promised 50 people. I'm disappointed. They could keep trickling in. You know? I think they probably will. Yeah. I need softballs, not hard questions, right? I'll just defer them back to you guys anyway. The tough technical questions are going straight back. Maureen, it's 9:05. Do I need to get started?
Good morning, everyone. Welcome to Embedded to Open Source Summit. Our first speaker today is Brendan Slade from NXP.
Thank you, Maureen. Everyone hear me okay at the back there? Yep, gets nods. Okay, so as Maureen introduced me, I'm Brendan Slade. I'm based in San Jose, and I'm director of the horizontal enablement team in NXP's Secure Connected Edge business line. So my team looks after enablement related to software and tools that are broadly applicable across any application. And so that's why I'm involved in Zephyr as a broad-based enablement. And today I'm going to be talking about why NXP is doubling down on Zephyr, really about our experiences since the project began and why we're stepping up our resources and our engagement on the project because of how we see the market evolving. And so obviously making a gambling reference here. So am I a gambler? Well, I'm really not a gambler. I should say at this point, actually, I'm going to go back. I had some quite cool AI images that use me and David, but then turns out NXP is quite careful about things like that, and they said, you can't use any AI-generated images. So we've gone back to Shutterstock. So pictures you hear, you think, well, that doesn't look much like Brendan. Like, this doesn't look much like me. That's why. Anyway, I'm not a gambler. I don't like gambling. I never really have. And the thought of losing lots of money that I could be spending on something else for a few moments of a thrill really doesn't appeal to me. But David, my colleague down here, he's quite different. He's a very keen poker player. And it's interesting. I talked to a few people about poker and stuff. Apparently, it's very scientific these days. I always think about it in the 1970s and 80s movies growing up, where it was all about steely nerve and the poker face and a bit of luck. And David tells me, for him, it's kind of a combination of those things. Bit of science, bit of old school. So gambling, well, I'm not a huge fan of gambling, but even someone like me can enjoy a little flutter if the odds aren't so bad. So this is a horse called Red Rum. There's a race in the UK called the Grand National that's run for many years. It's a very tough horse race with a lot of jumping, and it's very unknown who's going to win. It's a bit of a lottery, but this horse won the thing 3 times. When I was a kid in the 70s, visiting Grandma, who was a bit more of a gambler, we would have a fun Saturday morning looking at all the runners and riders, picking out the ones we thought might win. And it was always a good idea to have red rum. You could get red rum and then an outsider. You were pretty safe in an each-way bet with red rum. Even if you didn't win, you still get some money back. So even I, as a gambling phobe, can enjoy a little gamble on something when I feel the odds are pretty good. But what has this got to do with Zephyr, you say? Well, any kind of investment by business in a project like Zephyr is a gamble. You're putting resources onto something on the belief that it's going to be a good return on investment. And so what I'm going to be talking about today is how we see the odds very much moving in the favor of investing more, and that's why we're doing that. And what exactly are we doing? So NXP was involved at the start of the Zephyr project back in 2016. And a big part of why we were doing that was some good vision from the leadership team at the time. The open source software adoption, we saw that increasing in the microcontroller market after obviously being so dominant in the microprocessor space. And it wasn't only an open source project, it was the fact that the project goals and objectives were very well aligned with NXP's. So the things have evolved somewhat since 2016, but not radically so. I think this is an extract from NXP's website looking at our strategic goals as a company, what we're trying to do. So we're trying to help companies be prepared for change. And as the market goes towards everything being aware and connected, smart, secure, and efficient, we want to make sure that our customers can leverage our products to adapt with that market. Zephyr aligns very well with a connected product market, and it also has a big focus on security and safety. So as the project's evolving, there's more and more happening with Zephyr with security and safety as well. That's continuing to evolve and align with what NXP's doing. So NXP is quite well known as automotive supplier, but we've been in the general market for a long time in many, many different application spaces with tens of thousands of customers. And we have got recently, just this year, we announced, or I wouldn't say repositioned ourselves, but we announced that there's a lot more investment in the industrial side applications now. So this, again, reinforces our work with Zephyr as well, and is one of the factors leading into the extra investment in that space. So in 2016, I'm going to put my glass on, so I can't read my speaker note. We came in as a platinum member, so we recognized that we needed to be committed enough to give the project a chance, right? If we didn't put enough behind it, there wouldn't be momentum, there wouldn't be critical mass to succeed. And so we did that, and we were involved in several working groups. We gradually increased the number of resources in the team over that time to do more in the technical committees and the working groups, and been contributing things like SDHC, DISC, and so on. Some of the people who've done that are here in the audience today. The team also supported NXP products. We did upstreaming the support. We saw some good contributions from others that supported some of our popular Kinetis devices, again, members in the audience who did that. And we focused on our IMX RT and LPT 5500 series devices because those were the ones most active in new designs, but we were also contributing to Kinetis parts and even some of the IMX parts as well were happening as well. But it was more of a, I wouldn't say ad hoc, but it was more of a background of adapting to what the customers were asking for and not going across our entire product line. And we saw steadily increasing levels of interest. As there was more customers, more activity, the whole project was growing, so we saw that looking healthy and good. So that was all fine. But then there was a bit of an inflection with COVID. So suddenly, there was obviously a massive human cost, and also for industry as well. A lot of companies really struggling, going under because they just couldn't get parts. So we saw this, once things had calmed down from the craziness, companies really looking at this supply issue. It really brought that sharply into focus. There were companies paying 10, even 100 times the market price for a product which may even be a gray market product. And this really made companies rethink. They'd been relying on products from one particular chip from one vendor, and then they were really paying the price for that. So they needed to change that so that they can adapt to different devices, and then companies really scrambling. It was very, very expensive and difficult for them to do that. So there was a recognition that they really needed to be able to adapt to the situation. So the pandemic has thankfully calmed down. The supply situation is pretty much back to normal. We're seeing normal lead times for semiconductors now. So why are we still seeing companies making a switch to Zephyr? And obviously they haven't forgotten already about what happened with COVID. But we feel there's more forces at play here than just the supply issue. This is based on customers that we've worked with that have made the decision to adopt Zephyr. So my picture here is showing a showroom with a lot of different appliances of lots of different variations. So if customers we've seen in a space like the appliance market, they were using whole sets of different micros from different places, different product architectures, and focused in on trying to either there's a historical thing, there's a non-organic growth of their product line, or they just had different groups working on different projects in different places. But we're seeing them changing to want to take the same code base and apply it across different products, even products using quite low-end microcontrollers. And to do that, they need to be able to reconfigure the design very easily and move across those different platforms to move quickly without having to just throw more R&D resources at the problem. And if you're going to deliver all these products, you still have to test them, even if you can reconfigure them and build them quickly. So you have that problem to solve as well. And again, there was a lot of legacy of test infrastructure that people were having to maintain and adapt. So people quite often criticize Zephyr for being complex, right? They say, oh, if I'm from a microcontroller background, what is this device tree, this kernel config? Why do I need to know this? The build system's so complicated. Why do I need to do this, right? But what we've observed is companies have really dug into that, looked at the bigger picture benefits, and once they've got over that learning curve, they can see that the transition from one product they're developing to another one is actually much simpler, because they just have to change the device tree and modify the kernel config, and they can target another platform very, very quickly, versus with other RTOSes, which may be simpler to use, but when you change to a different underlying processor, you have to go in and refactor the code. So there's more risk in terms of breaking things, and obviously more time. And on the test side, all companies have their own test infrastructure, right? They've typically grown it in the company, and they've adapted it for what they need. But the benefit of Zephyr having the infrastructure there to detect tests and to run them in a standardized way provides that for you, and you get the benefit of working with a community. So you can upgrade everything together with that community rather than having to rebuild it for your own personal use or as you change different platforms. So we see the customers recognizing these benefits and making it a stronger case for them to adopt Zephyr. So with NXP's portfolio, one of our strengths is we have a very broad range of products. We have some very low-end flash-based micros up to very high-performance crossover MCUs, and then our IMX SoCs with Cortex-A, Cortex-M cores inside. What we see is the customers want to leverage this portfolio. They want to have multiple sources, multiple vendor partnerships, but not too many. So they still want to try and leverage a portfolio like this. They want to be able to make use of new technology as it comes out, either for cost reduction purposes or for introducing new features like ML. And they want to be able to make the right energy performance trade-offs. And on the IMX side, it's quite interesting that we're seeing, we've been promoting the concept of moving between IMX and IMX RT for quite some time. But we're really seeing that happening now in a couple of ways. Customers have a microprocessor-based design. For example, like in our EVSE charging solutions, we see customers having an MPU-based design, but they want to cost reduce. They want a lower-end solution, and they really want to use IMX RT for that. We see it in the appliance space as well, in smartwatches. All of these spaces where, for a combination of cost and power, they want to make that move down to the crossover MCUs. But we also see in the IMX side people wanting more performance. So they're actually going up from a 600 megahertz Cortex-M7 up to a Cortex-A because they need more performance. And by having a consistent strategy with our different platforms and enablement of those platforms, it makes that transition much easier. And for people my background is more on the microcontroller side, but I've heard several anecdotal conversations about Linux developers saying, oh yeah, I get this. It's much more familiar than an RTOS like ThreadX or FreeRTOS and so on. So the alignment, again, with NXP and what Zephyr brings is a very good one, because Zephyr really lends itself to leveraging our portfolio. So that's a big plus for us and for our customers. Cyber resiliency laws, right? So these are right now in our faces, right? So things are changing. The legislation rules. We've seen quite slow take-up of security, to be honest. You'll see companies that are very much on it and have been for some time, and then other companies that kind of been running away screaming for quite a long time, but now they have to face it. So obviously having a strategy that is going to encompass security is important, and Zephyr has that. But one of the other aspects of this is the longevity of support, and this is less obvious. The legislation's requiring 5 years of support or the expected lifetime of the product, which could be 10 or even more years, right? So for an OEM that's been relying on an RTOS, a commercial RTOS or another open source one, where the destiny of that RTOS is controlled by one company or is small or it's proprietary, that becomes a risk. This isn't a criticism of those other RTOSs. There's some that have been out for a very long time, and they have a good support model for security and long-term support. So they do exist out there, but this is one thing we see customers concerned about, that they're worried that the destiny of that RTOS company is too much out of their hands. And with the momentum and the number of companies behind Zephyr, it's a much more comfortable position to be in, to be aligned with Zephyr. So back to more of NXP's interests. So we're moving to add value beyond our silicon. So we do a lot of very clever things in our silicon, but we want to bring more value by bringing enabling technologies to customers so they can really differentiate much more quickly and effectively. So this is areas like graphics or networking or motor control and these kind of things where we can provide a lot of the building blocks that they need, which have differentiation, but not to the level that the differentiation value, multiplying effect for them is lower than if they can just focus on their high-end application. And so for us, we want to offer example integrations, say combining a motor control with a networking application. We have things like that. We have a quad motor control demo that does that over a TSN network. So we show how to integrate those pieces together, that kind of example. And as we do more and more of these, we have to pick a platform. We can't just do it on all platforms all the time. That's just too much. But by building on top of Zephyr, we can much more easily adapt to a particular customer saying, oh, I love that, but I want it on this instead. So we can do that. The picture there is from our application code hub, which is a way to kind of sort through our application examples. You can filter by Zephyr. We're just starting to add Zephyr examples to this, so there aren't so many there yet, but there will be a lot more coming over the next few years. And one of the other nice things, apart from the ability to be flexible and adaptable to move to different platforms, is we don't have to give up the differentiation of our underlying hardware. So there's another talk from NXP later this week by Disha Patil, where she's going to be talking about an IMX-RT 500 and power optimization on that. And that nicely illustrates how voltage scaling on that particular product can be leveraged for very low power. And it also doesn't mean that that entire project is completely locked into that device. Let's get a swig of water. Okay, so I'm going to give an example here. Now, this is a demo that we have on display this week at the Solutions Showcase. I talked about IMX-RT 10XX. Well, this is an RT 1060 used in this demo. We also have done a lot of promotion at Embedded World last week about the MCX family, the MCX-N family. But they're quite different architectures. So the RT products are based on the Cortex-M7. They're based on a process that doesn't support flash, but can run a lot faster. We introduced this concept, I know, I'm trying to remember, it was about 5 years ago now, and it's done very well. Obviously, those devices rely on all off-chip non-volatile memory, so they have a quad SPI flash interface. They also have an SDRAM interface, which is obviously not non-volatile. And they have a lot of peripheral IP in common with IMX SoCs. And that's in contrast to the MCXN family, which has more of a lineage from our LPC and Kinetis processors. That's where that peripheral IP comes from. It's more traditional in the sense of having a on-chip flash, has great improvements in cache and other things like that to get more performance out of the core frequency in the memory. But basically, it's that kind of lineage, that kind of device. So the core runs a lot slower. It's 150 megahertz versus 600 megahertz. But it has much lower power consumption. And the MCXN family also has a neural processing unit as well for ML applications, obviously. So the demo that we have actually runs the same application on both of those platforms. So that handsome face is Derek Snell, who will quite happily talk you through the demo later if you want to come by the solutions showcase. So on the right-hand side, there is the RT1060 with the LCD panel mounted to it. And on the left-hand side is the MCXN board, and that's using a quite different kind of display. The application also handles the portrait versus landscape orientation as well, and the text positioning too. So the MCXN demo leverages the NPU hardware for faster inference times. So you can see the numbers on the screens if you squint a bit, but basically the RT1060 is running at 600 megahertz, and running a ML model that's purely implemented in C. And the MCXN is using the NPU, and our tools take the same TF-like model and compile it down to make optimal use of the NPU. But the actual source code, again, is the same. We use a binary blob that we create, and that hooks in to actually run the code on the NPU. So that's how that's different. But it's still starting from the same model. And the interfaces between all these, between the display and the camera, are very different on these two devices. So here's a high-level block diagram with the hyperlinks for the particular hardware in case you're interested in following up, looking more. So on the left-hand side, you see the RT1060 eval board, and it hooks up with MIPI CSI and I2C for the camera control. On the LCD, it has a built-in LCD interface, whereas the MCXN, which isn't designed as much for HMI applications as the 1060 is, but it can still do a pretty decent job with the display, uses this block called FlexIO, which is like a configurable logic block, if you like, so it can do a lot of different things, including driving this kind of parallel display interface. And then on the camera side, the MCX also has another block called Smart DMA, which is useful for handling things like cameras, and the same I2C interface. So quite different hardware configurations between those two. But if we look at the actual software stack, everything from the kernel above is the same. So we're not changing any of that. All of the interfacing into the hardware is done below that kernel level. So the shim drivers, these translate an NXP proprietary SDK API, our MC-Expresso SDK, for those who know our other software products, translates to the Zephyr HAL. And so this is what NXP provides, and then everything below, obviously, is proprietary to the different platforms. But NXP is providing all that enablement for you. So we have learned some things along the way. We did actually augment the display driver so it could handle a device which has got a lot of RAM and can handle the frame buffer easily internally. That's the 1060, versus another setup with the MCXN where you had to break the image down into strips. But you know, it's the kind of thing you learn and you contribute back to the project. So that's what we're doing for that. But we've proven that you can make an application like this, which is quite different in terms of underlying hardware, and the acceleration capabilities run on from the same code base. So I did want to mention also what we're doing around the developer experience. So we recognize that the build system and so on can be a bit confusing for people. There's a lot of different tools you need, like West and CMake and all these other things that normally people are used to installing an IDE and it's just there, right? So we know that's a bit confusing for people who maybe don't come from a Linux background. So what we've done is we introduced support for, an extension for VS Code last year, which was for general use, but we always had the intention of focusing on Zephyr and improving that developer experience. So that's what we're doing on an ongoing basis. And we, along with this, is not on the slide here, but we have an installer. So that helps you install all the different pieces you need to make life easier. And we welcome any feedback on that. We're trying to keep improving it and make it better. We put quite a bit of work into our link server, which is our proprietary debugger GDB server and other utility that gives people an option along with the Sega, which JLink is obviously very popular in the project, so we support that as well. And our area of focus going forward is how do we make things easier for people who aren't so familiar with device tree, where it can be error prone when you're editing a device tree, and you can make mistakes. We're trying to figure out how we can make that better. So anyone's got any suggestions, come and chat to us. We'd love to hear about that. Nordic's done some good things in that area too, so we're watching what they're doing, interested in what people think about that. Main point though is that rather than just doing platform support, the developer experience is something we see as very important as well, and we're trying to help those people ease the transition from traditional microcontroller development. Another area that really helps is the collaboration with the project and what that brings to the customer experience. So for us, there's a debt reduction. We don't have to spend as much time working on kind of table stakes, going back to a betting reference again, I guess, for supporting important stacks, but ones that aren't really differentiating for us or for a competition. So we can work together to generally improve the quality of things like USB and file systems and so on. But that also frees up some of the resources we would have had to put on that to focus those on developing new features that are really going to help the customer and help us make the most of the hardware capabilities that we're delivering in our products. And then community support. I think I've got a long history in applications, and customer experience is very important to me. And by having a community approach to this, rather than having people go to the NXP community, we send them to the Zephyr community and we answer the questions there, because we see the benefit to everybody of behaving in that way. So we really see that as a great way of working, and we appreciate all the Zephyr members that jump in and help each other out as well. It's a great model, and it is working, is what we see. So how is NXP doubling down? Well, we're moving from this kind of what you might call an incubator model, where we have a core team that's been doing a lot on the project for some time, but supporting platforms as they could, to one where Zephyr enablement is mainstream for us, meaning that all our new products coming out from the Secure Connected Edge business line will have Zephyr enablement as a standard thing. So when the product comes out, Zephyr enablement will be there, or will come very soon after the product launch. You've seen it with the MCX N series. We put a lot of promotion around that. We're upstreaming support for that right now. And we're working with DoLOS, AC6, others to really provide that as a platform for people to get a low-cost board and be able to get started on that. But it won't just be that. We plan to do it across all our microcontrollers, apart from the very low-end ones. But even there, we're seeing customers. We didn't expect customers to want to have Zephyr enablement on the very low-end and micros, but it's happening, and we're responding to customers in that way. Greater investment engagement, that means more about our own organization getting trained up more, so our own FAEs and our own systems engineering teams, but also getting more involved in the Zephyr meetups and so on. So we're going to see us doing more and more around those things. And back in the way that we make the sausage, the way we typically work historically has been our SDKs are developed as these packages, these archive files, which when we do a release every 6 months, we generate a package like this, and everything's kind of geared around that. We're completely reworking that. So we've had SDK being pushed that onto GitHub for some time now. It's proving very popular. And we're changing things around so GitHub comes first, not last. And that's going to make everything easier to get the Zephyr enablement much faster as well. So that's happening right now. It takes some time to change the plumbing around to do that, but we're very actively working on that right now. So, and we're also going to see more downstreaming of platform support. So we're very much in favor of upstreaming. That's our fundamental approach, but we want to downstream platform support so customers can access it earlier. But I do want to emphasize we're very much in line with an upstream support model. With the IMX products, we've been doing some things a little bit more ad hoc, where different groups have looked at Zephyr and they've used it for various different reasons. So we have our real-time edge software framework, which was derived from OpenIL. And we're trying to have that align with the Zephyr project, the other aspects of the Zephyr project more closely. So what RT Edge gives you is a configurable multi-core framework, so it really leverages multi-core interprocessor communication with a target for industrial applications, a lot of networking and motor control and things like this. So we're working hard to get that better aligned so our roadmap for IMX becomes much clearer. That's something we're working on right now. And as I mentioned in the last slide, we're investing a lot more in the developer experience, and we're very open to hear what people have to say. Okay, so all of this, coming back to the whole gambling thing, I feel pretty good about this. I'm a real Zephyr convert. I'm probably a fanboy at this stage, and I can sleep much better at night. I feel pretty comfortable with the bet we're making. So, there we go. There's my Zephyr. Dreamy of Zephyr. All right. Well, thanks everyone for your attention. I'll be in and around the different papers and the solutions section as well. Appreciate any feedback you guys might have. I hope you found this useful. The intention was to share our experiences and you know, where we're going and why we're going there. But we're keen to hear what you guys think as well, and any points we may have missed that were really critical to you. I know I didn't say a lot about safety. That's a very big thing for us as well. I didn't focus in on safety in this, but you know, that's another important area for us too. So thanks everyone. I don't know if there's any questions. Yes.
And for those watching on the live chat, you can post questions, or sorry, on the live stream, you can post questions on the chat, and I'll repeat the question to the speaker.
Okay, thank you for your presentation. So my question is, how Zephyr and your portfolio of different offerings coexist with all the rest, FreeRTOS, ThreadX, whatever?
Yeah, so it's important to note that NXP is kind of neutral when it comes to an RTOS implementation. We're not going an all-out Zephyr and nothing else, right? We are still providing free RTOS support because it is still the most popular RTOS in the market, right? But we see those as kind of parallel to each other. We do have commonality, and we have our SDK that we've always had, our proprietary SDK, but our current model is we shim that to match Zephyr. So that remains a common piece, and we continue to support free RTOS as well. When it comes to other RTOSes, we would tend to leave those to the community to support them. We have various degrees of involvement with them, but our main focus is on Zephyr enablement, free RTOS enablement.
Okay, thank you.
Still too early in the morning. Not enough coffee yet, right?
We do not have any questions in the chat, so thank you, Brendan.
All right, thanks everyone. Thank you.
Good morning, everyone. Our next speaker today is Jason Murphy from Analog Devices.
Good morning, everyone. Good morning, everyone. Is that working? Good morning. Okay, get that. Good morning. Is that audible? Not really. Maybe I'll just use one of these. Good morning. Okay, there we go. Okay, hi everyone. So yeah, my name is Jason Murphy from Analog Devices. So I've been with ADI for about 4 years in total. My background is in embedded software and system development in the domain of industrial automation primarily. So working on technologies in the building automation space, industrial connectivity. And for I guess about a year or so now, I've been working with Zephyr, primarily in the context of single pair Ethernet. So that's what today's talk is going to be about, enabling real-time secure connectivity to the edge with single pair Ethernet and Zephyr OS. So just for an agenda for this talk, I'm going to kick off with an intro to 10BASE-T1L single pair Ethernet. I'll discuss this technology, what it's all about, the use cases, and why you might consider using it for a project or a device. We'll then look at the importance of software and the need for software when developing solutions and devices based on 10BASE-T1L connectivity. And then look at Zephyr and look at why Zephyr is a great choice when developing these types of applications. Okay. So let me begin with some background into this technology and why it exists. So I guess I'm sure everyone here is pretty much familiar with the concept of Industry 4.0, the digitalization of industrial, factory, and building automation environments. And so, in general, there's a demand for more interconnected devices and data-driven decision-making. As you can imagine, industrial networks play a very important role here in facilitating this. And over the last number of decades, Ethernet has been adopted in these industrial networks where possible as a standardized communication technology. So while Ethernet has been adopted where possible in these networks, primarily at the backbone of these networks, at what's known as the control level and at the enterprise level, as you see on the slide here, a gap existed in bringing Ethernet to the edge. And so in 2019, the IEEE ratified the 802.3 CG standard for 10BASE-T1L single pair Ethernet, which is a new physical layer standard defined really in enabling Ethernet connectivity to edge devices. So what is 10BASE-T1L? Well, you can summarize it with 4 key things really. It's 10 megabit per second Ethernet that operates over distances up to 1 kilometer that can also carry power and data and all over a single twisted pair of cabling. So that's just 2 wires. So the image on the right side there shows, I guess, a representation of where 10BASE-T1L would sit in a typical industrial network. So like I said, while your backbone, your enterprise and cloud and control levels will remain with standard and gigabit industrial Ethernet, as this Ethernet network extends to the far reaches of industrial environments, think sensor and actuator type devices, 10BASE-T1L extends that physical layer to these types of devices. So the result really is a network that converges completely on Ethernet with a seamless link from the edge to the cloud. So just to go into some more detail about 10BASE-T1L and the key benefits of this technology. So I'm going to look at this in 4 key areas, including data rate or throughput, bringing IP to the edge, security, and diagnostics. So with data rate, so 10 megabits per second, you're probably saying, we have gigabit Ethernet these days, it's nothing impressive. The key thing to consider here is the comparison to the legacy field bus protocols, which 10BASE-T1L is replacing. So if you consider a technology such as RS-485, for example, a serial bus, over distances of like 1 kilometer, RS-485 would be operating in the kilobit per second range. So 10 megabits per second is a sizable improvement here, and is oftentimes plenty of data rate for sensor type and edge device applications. The improved latency is also important for applications where low latency networking is critical, such as control loops where there is often a desire for millisecond latency. The next thing is IP to the edge. So this really is a key factor with 10BASE-T1L. I mentioned the converging of networks on Ethernet throughout. So with 10BASE-T1L, the entire industrial network can converge on Ethernet connectivity, all the way from your enterprise cloud level down to your edge devices. As it stands, industrial networks are often fragmented in that there is varying technologies used throughout, which requires complex translation systems and gateways to convert between these technologies, which results in siloed data or data islands. By moving towards Ethernet, the entire network can converge on Ethernet and really simplifies data access throughout. Next is security. So again, in the industrial space, as the IT world and the OT world, which is the operational technology, or so factory floor technology, let's think about it like that. As these technologies converge, security becomes increasingly important because, as you can imagine, the ability for external attackers to access this OT technology through the IT domain increases. Thus, it is really important that modern cybersecurity techniques are deployed to the operational network. And then finally, diagnostics. The key thing here is that Ethernet is full duplex connectivity. Again, in comparison to the legacy field bus protocols like RS-485, these protocols are often limited, or half duplex, can only send limited amounts of data at one time. With Ethernet, we open the door to more complex data, device-centric data being sent, such as device data, diagnostic data, and even implementing features such as over-the-air updates, or I guess over-the-wire updates. Okay, so at ADI we have a portfolio of 10BASE-T1L transceiver products. There's 3 in total. So just to quickly highlight what these are, and to give context to, I guess, the software piece, there is a MAC PHY, and a 2-port switch. So each, I guess, has a slightly different use case and application depending on what you're trying to do. The PHY will be primarily used in more high-performance applications where a more high-performance processor is in place. The requirement here is that your processor has an onboard Ethernet MAC. And so the interface between the processor and this PHY will be done using RMII. I guess what I want to talk more about today is the MAC PHY and the 2-port switch products. With these products, they include an onboard Ethernet MAC, and the interface to the microcontroller is done using SPI. So this opens the doors to adding 10BASE-T1L single-pair Ethernet connectivity to simple microcontroller type devices, ARM Cortex M0, M4, pretty simple MCUs that do not include an onboard Ethernet MAC. And really that's kind of what I want to talk about today in the context of Zephyr. Okay, so while we have these 10BASE-T1L transceiver PHYs and MAC PHYs, enabling an embedded device with Ethernet goes beyond the physical layer. And it can be a challenge to do so. When we consider the EOSS model that represents the layers in a networking stack, we see that the Ethernet standard itself defines only the physical and data link layers. And everything from layer 3 upwards is purely software defined. So that kind of gives you an insight into the importance of that software plays. Outside of this, key connectivity, key software components include things like device drivers for communicating between the host processor and the PHY or MAC PHY. The connectivity stack, and this is, again, a key requirement from a software standpoint. The TCP/IP suite is pretty much the de facto standard when it comes to implementing networking connectivity these days, and it's vitally important that embedded devices have a full TCP/IP stack to ensure that they are interoperable with existing IP networks. Next is application protocols. So this will be application dependent, but common application protocols like MQTT, HTTP, CoAP, lightweight M2M, again, are all software defined. And finally, there's also a trend, generally speaking, towards carrying out more processing at the edge, so decentralizing software. And so it's something to consider that these edge devices are being tasked with increasing processing loads. So that's where our friend Zephyr enters the equation. Really, I see Zephyr as a highly suitable embedded software ecosystem to enable the development of embedded systems and devices with 10BASE-T1L connectivity. So I'm going to go ahead now and look at why Zephyr is a good choice, and then look at how 10base-T1L is supported within Zephyr and how you can develop applications with Zephyr and 10base-T1L. Okay, so why Zephyr? Well, there's a couple of reasons for this. I think generally speaking, people associate Zephyr with wireless communication most prominently. Zephyr is highly prominent in the IoT domain with wireless technologies like Wi-Fi, LoRa, Bluetooth, etc. But primarily the same software can be deployed for wired applications also. And this is very true of the TCP/IP networking stack that Zephyr provides. So this stack provides support for the key protocols required when enabling a device with Ethernet connectivity, from layer 3, layer 4 network transport layers all the way to various support for layer 7 application protocols. Zephyr's stack is also native, meaning that it was developed specifically for Zephyr, with common memory buffers being used throughout, which is advantageous in terms of reducing RAM usage, which can be an issue when implementing TCP/IP connectivity on embedded devices. The real-time performance is also a factor to consider. So Zephyr obviously is an RTOS, and while it's not always a hard requirement to have real-time capabilities on embedded systems like this, implementing low latency networking is often a requirement for industrial applications. So Zephyr provides those capabilities. Resource efficiency is also it's a factor in lots of embedded systems, but again, when you're considering pushing connectivity to the edge where you have a simple MCU, ARM Cortex M0, M4 with limited RAM and flash, resource efficiency is critical. So Zephyr is highly optimized for these types of applications. And then security. So I've touched on the importance of security. As the IT and OT domains converge, it's very important that modern security techniques in terms of data encryption over the Ethernet link, as well as device authentication, are deployed. And again, Zephyr provides all the key components here. And then being open source and being portable are things that aren't specific to this application, but are obviously very nice to have. From a portability perspective, I think that the ability to reuse application code, networking application code, that's agnostic to the physical layer. So for example, the ability to reuse application code that was developed for a Wi-Fi physical layer with Ethernet is highly advantageous. Okay, so now I want to look at how 10base-T1L is supported within Zephyr. And so, like I said, Zephyr is more associated generally with wireless communication, but it does have quite a good level of support in place for Ethernet. And so Zephyr defines a standard layer 1 API for Ethernet devices. So supporting the 10base-T1L physical layer, supporting a 10base-T1L transceiver in Zephyr is really just a case of implementing the standard layer 1 API. And this abstracts away all of the common and the complex details of the physical layer away from the upper layers of Zephyr's networking stack. So just the image on the right side shows the interface between the host MCU and the MAC-PHY. There is a standard 4Y SPI interface along with 2 GPIO pins for interrupt processing and to reset the device. So the standard API is shown here on the slide. It's a pretty simple API, generally speaking. There's APIs to start and stop the interface, to get its hardware capabilities. So this is information pertaining to the physical layer, like its throughput, if it's 10 megabit, 100 megabit, etc. If it supports promiscuous modes, auto negotiation, for example. There's an API to set the config of the device, and then finally to actually send data to the physical layer. So really, supporting a 10base-T1L transceiver within Zephyr is a case of implementing a driver which defines these APIs. The initialization function, I took a snippet here from the ADIN 2111 driver from Zephyr. And so the key things that this type of driver function will do will be to check the SPI interface between the MCU and the MAC-PHY, configure, reset, and interrupt GPIOs. So these will have associated callback functions which will be used to handle data being received over the physical layer, a soft reset, and then finally creating an offload thread. So a common approach within Zephyr Ethernet drivers is to create dedicated threads in the driver layer, which will be responsible for handling data received over the physical layer. These threads will be synchronized on interrupts from the device, which will then allow the thread to go ahead and read data from the receiving FIFOs. Okay. In the context also of driver support for these devices within Zephyr, I want to highlight a recent addition to Zephyr, which was recently merged upstream in the past couple of months, and this is support for the Open Alliance SPI interface. So Open Alliance is a kind of special interest group, which is really focused on pushing the use of Ethernet in industrial and automotive applications. So this special interest group defined a standard 10BASE-T1X MAC-PHY serial interface. So T1X means that it supports both 10BASE-T1L long-range Ethernet as well as 10BASE-T1S short-range Ethernet, which is primarily used in automotive applications. The benefit of this MAC-PHY interface is that it enables full 10 megabits per second frame transfer with an SPI clock of around 12 to 16 megahertz. So to achieve full 10 megabits per second frame transfer using standard SPI would require your host processor to operate its SPI peripheral with a frequency of near 25 megahertz. So having support for this Open Alliance SPI within Zephyr is great to see. It's great to see that there is, the open source community are out there and using 10BASE-T1X. Okay, so then now let's look at Ethernet application development within Zephyr for 10BASE-T1L. And so there's four key points to this, four key things that one must do. These are platform selection, board config or hardware config, software configuration, and then finally moving to application development. So first up is platform selection. So there is currently support for two of ADI's 10BASE-T1L transceivers within Zephyr. These are the ADIN 1110 MAC-PHY as well as the ADIN 2111 two-port switch. So these transceivers, along with their respective evaluation kits, are supported within upstream Zephyr. You can see their location in the drivers directory. So these evaluation kits have onboard STM32L4 MCUs with some things like temperature sensors, for example, which are useful when developing kind of proof of concept applications. So these boards will be a great starting point for developers looking to get started with 10BASE-T1L within Zephyr. Of course, you have the option to interface to any host processor of your choice using the exposed SPI headers on these boards. So once you choose your platform, next up is device tree configuration. So I've included a snippet here from device tree for the ADIN 1110 MAC-PHY. And so, for those familiar with device tree, there's nothing new here, but the key things we're configuring are the SPI interface, the SPI bus we are using, the reset and interrupt pin configuration, the SPI frequency, along with the DMA config if DMA is being used. And obviously using DMA in an application like this, where we're frequently reading and writing to the SPI bus, will be advantageous. The MAC address of the device is also specified here in device tree, as well as the Ethernet LED functionality. So these MAC-PHY products have onboard LED GPIOs, which can be used to signify things like the traffic on the network. So once device tree config is done, we move to software config using kconfig. And really here it's a case of choosing your protocols that you want to use in your Zephyr application with Ethernet. The key kconfig symbols that must be defined for Ethernet support are shown here in the box. So Ethernet driver layer, the support for the ADIN driver part itself, as well as the layer 2 API for Ethernet. And everything beyond this really is application dependent, be it you're using IPv4, IPv6, or both. You may use TCP or UDP. In this case, we're using DHCP also, along with sockets and MQTT connectivity. So as you can see, Zephyr supports many of the key layer 2, layer 3, and layer 4 protocols, which are important when developing applications with Ethernet. Okay, so then after that, you're free to move to application development. So for those who have worked with Zephyr, Zephyr's networking stack for be it with Wi-Fi or 802.15.4, whatever physical layer, the same, APIs and libraries can be deployed with single pair Ethernet, so nothing changes here. And I think this is kind of one of the beauties of Zephyr, the ability to reuse code across different physical layers without the need for much porting. So Zephyr, has support for the BSC socket API, MQTT, HTTP, lightweight M2M, and CoAP. Again, lots of these are highly industrial focused, which is great in the context of 10BASE-T1L. I think for developers also who are looking to move to maybe working on a product with industrial connectivity, who have experience with socket programming, this opens the doors to reuse your existing knowledge, your existing know-how with socket programming or MQTT, for example, with an industrial focused communication technology. Other protocols that Zephyr supports, which are really useful for these types of applications, are things like DNS, DHCP, the JSON library, which is important when communicating with the cloud. The network management library is great for when developing, for handling networking events that happen throughout the program. And then zperf is great for managing throughput and measurement of latency of your network. Okay. I also want to highlight securing Ethernet connectivity. So Zephyr provides support for the TLS protocol using embed TLS. Like I touched on earlier, the importance of TLS is there given the importance of security in the IT as the IT and OT domains are converging. Zephyr makes it really easy to enable TLS security over Ethernet using standardized APIs. If you've ever tried, spend time configuring embed TLS outside of Zephyr in the bare metal environment and spend time, integrating it with a TCP/IP stack, etc., having this pre-integrated and the ability to move directly to application code development is very, very valuable. Okay, so just want to highlight an application that I've spent some time working on recently. So I currently have a PR open to merge this as a sample application upstream. It's really serves as a reference design for customers looking to get started on 10BASE-T1L connectivity. So I've tested this on the eval kit for the ADIN 1110. And it really pulls together, software with some of Zephyr's key components, including, MQTT, DHCP. So essentially, the key features: it acquires an IP address using DHCP, brings up a secure MQTT connection using a secure socket connection, and then subscribes to user-defined topics. And there's threads that are dedicated to publishing temperature sensor data at regular intervals, along with dedicated threads for handling the incoming MQTT data. So this application shows what you can achieve quite quickly with Zephyr and when developing applications for 10BASE-T1L. Okay, so that brings us to the end of the presentation. I'll summarize but these key 3 points. So 10BASE-T1L single pair Ethernet is bringing long-range Ethernet to the edge with 10 megabit per second data rate. But however, enabling these edge devices with Ethernet connectivity, it goes beyond the transceiver, and software plays a really important role. And Zephyr is a great embedded software ecosystem to enable the development of edge-connected devices with Ethernet connectivity, thanks to its native TCP/IP networking stack, its security capabilities, and its real-time capabilities. So Zephyr is already SPE is already quite well supported within Zephyr. So I think if you're considering your next project and require robust, secure connectivity in the wired domain, why not consider 10BASE-T1L and Zephyr? Thank you very much. We also have a demo at the ADI booth showing a Zephyr with 10BASE-T1L, so it's booth E15. If you're interested, you can drop by for a conversation. Thank you.
Thank you, Jason. For folks in the room, if you have questions, I'll bring a mic over to you. If you're watching the live stream, please feel free to post questions in the chat, and I will repeat the question out so the speaker can hear it. Thanks.
Yeah, I was curious. A very good presentation, and I agree that single pair Ethernet is going to have a big play in many of these embedded markets. You talked about real-time and industrial. I'm curious how you see in the software stack, TSN is a big part of those stacks in this. How do you see Zephyr's support for TSN in there? I mean, TCP/IP is not exactly real-time, so I'm curious what your experience there is and if there's more development needed in that area.
Yeah, it's a good question. I think TSN, yeah, you're right. It's kind of the next advancement, I think, in industrial Ethernet. So to the best of my knowledge, Zephyr doesn't have support for TSN connectivity. So generally speaking, I do think support for TSN is something that, in the context of Zephyr and ecosystems like Zephyr, it would require, I guess, a kind of a maintainers to kind of come together and look at how support for TSN could be done from a software standpoint. It's not something I'm too familiar with, so I guess I don't want to comment in too much detail, as it's not something I'm very familiar with.
We don't have any questions on the chat. Thank you, Jason.
Thanks, everyone.
type the right port. Okay. So on my machine, I'm going to use a co-op client for getting a resource. So you use it a bit like HTTP. You want to get a value, I don't know. Oh, okay, so it doesn't exist. I get a 400 error. Or if I give a real URL, no, is that the typo? Yeah, I get a response. Quickly, without going too much into the details, and explain why co-op can be confusing, because it's combining the reliability layer and the request response scheme in the same packets. So, for example, when I did the first get from the client, so I issue a get with this message ID, so 43634, and I have a token. So you have two identifiers. You have one, the message ID, and one which is a token. And you get a response with an error code, but with the same message ID and the same token. So the token is used to correlate the request and the response at the REST level, so the get and the response. And the message ID is for reliability. Basically, the first message is a confirmable message, so it's expecting a ACK for the same message ID. And you can see on the second one, I'm issuing a get, but the server is going to behave differently. It's going to first acknowledge the request to say, I received your message, you don't need to retransmit it. And then later send the content back, asking also a confirmation, an acknowledgement from the server. So in place of doing the transaction in 2 packets, here it's done in 4 packets. So yeah, it's due to the fact that you can decide how you want to handle the reliability of your message. If you want to take some time before building the response. And yeah, and that's why I find the co-op a bit confusing. Yes, and then yeah, you find exactly what you can find with HTTP. So you can get URI, you receive response code, you have methods. So the goal of co-op here is really to replace 2 protocols in one, so TCP and HTTP, and something compact and fitting low-power networks and constrained devices. So that's why I say it's not a general-purpose protocol like, I don't know, HTTP or MQTT. The goal of co-op is really to target this kind of devices and application. Another feature is block-wise transfer. So since you are using UDP, if your packet is larger than a UDP packet or the capability of the device, for example, if your device don't have a lot of memory, you don't want to send a 1 kilobyte payload, maybe you want to send a 200 or 500 payload. What co-op is doing, which is a bit different of what TCP is doing, it's having a very simple approach to block-wise transfer. So you send a first, for example, a first get for downloading something on the device. The device will send you back the first block and say, okay, this is the first block of n blocks. I have 20 more blocks to send to you. So then the client is going to iterate, ask the next block, get the block, etc., etc. So what is the main benefits? It's very simple. It's very simple to implement. The main drawback is as soon as you want to send megabytes, it's going to be very slow, especially if you have high latency. For example, if you have alpha seconds latency, which is common on this kind of network, every block we need a round trip of alpha second. And so if you need to move 1 megabyte, it's going to take a long time, which is different of what TCP is doing, because TCP has this concept of ACK windows, which is slowly opening, sending more and more packets in flight, in parallel, and optimizing a bit the bandwidth. So it's something to take care with co-op. If you want to transfer a lot of data, you need to be careful. It's going to take more time than TCP, for example. Quickly on the security, it's basically you need to use DTLS. You have another solution, which is EOSS Core, but EOSS Core is not very popular. I would say there is not a lot of open source implementation. The main benefit of DTLS is that you need to do this uncheck, which is going, of course, to cost you time and bandwidth. But you have a nice protection against denial of service, but also you can support multiple cipher suite, and you are able to negotiate with the device different way to secure it. So you can have a system that is basically going to evolve from one cipher suite to another cipher suite later if you have a security issue. Now the quite ugly part of using a UDP protocol when you want to do something a bit more complicated than what I did. So what I did here is you have the co-op server exposing the resources, the device, and you have the client, which is going to issue requests to the device. When you want to start connecting this system to the cloud and not just interacting locally with maybe the device connected to the local network, it will take some the device to stop acting only as a server, but also acting as a client, sending, for example, a post to the server to send, I don't know, telemetry data or something. So when you do that, and in the middle of your internet connection, you have a router which is going to translate the public IP of the network into the private IP of your local network. It's going to put a session for the server to be able to send back packets back to the client. So the client sends a message, the server sends back a response. But if the server wants to send back a request to the client, it needs to do it in some given amount of time before the session is gone. And what is tricky is for TCP, most of the router you have in the wild, they keep session for more than 50 minutes. It's more hours than minutes. For UDP, because UDP is mostly used for DNS and voice over IP or conferences software or this kind of application, the timeout is very low. It's like 3 minutes normally, and sometimes as bad as 30 seconds. So you have basically, when a device sends a message to you, then you have a window of 30 seconds to send back requests and interacting with the device. And after 30 seconds, the device is not reachable. You need to wait for the device to come back. So, so it's where it's blurring the line with HTTP and this concept of co-op server and co-op client. Typically, when you want to connect this kind of devices to the cloud, you need to have the device acting as a co-op client, posting some values to the server, and doing it regularly if you want to maintain a connection. Maybe you don't want to maintain a connection, it's not a problem. Maybe you will port the server once a day or something like that, which would be fine for a smart metering application. But if you want to maintain a connection, yeah, you need to send a packet regularly. And then, yeah, then the server is able to interact with the device, reading the resources on the device, rewriting resources on the device, for example, for reconfiguring the device or interacting with the device. Yes, so it's a tricky problem. So for example, for home automation style application, since you don't really control the network, You don't really control what kind of internet service provider the end user is going to use, what kind of Wi-Fi router. Maybe they pile up 2 Wi-Fi routers. You can imagine all the complexity of that. So you need to use either keep alive, so having the device pushing data all the time to keep the device, the server, and the device connected and be able to send back packets to the device. Typically with this kind of application, for example, if you have a phone application connected to the server, and you want to interact in real time with the device, you have no choice. You need to keep the connection open. Or if you don't have the needs for this kind of interaction, you can buffer the operation of the cloud and wait for the next polling from the device. So that's one network topology where co-op is used. So it's not a problem. It's not a problem. It works to do this for this kind of low power network like 6LoWPAN or Matter thread because it's a local area network. You refresh always the connection anyway every 3 seconds. So it's not going to add a lot of battery usage on your device. But for cellular-based application, where you use a 4G low-power modem, for example, it's a bit complicated because every packet costs you a lot. So it's not practical to send a message every 30 seconds. But you can use different solutions. So either, you use some queuing system and you say, my device is just going to poll from time to time and I'm not going to maintain a connection. You can maybe try to use the good old SMS for forcing the device to reconnect when you want to interact with the device. It's a bit tricky to secure, but it works. Or you can ask your connectivity provider, your mobile network operator, or the people who are selling you a SIM card, to create a private network for you. So it's a software-defined network they build on top of the public network. And in this private network, you will be able to select your IP address and remove totally the NAT from the picture. So you will not have anymore the problem of the NAT timeout. You can also try to use TCP-based system if you can handle the performance issue which come with using TCP on this kind of lossy network. Obviously the right solution would be IPv6 in both cases, but we are not there yet. One word about lightweight M2M. So lightweight M2M is a device management standard built on top of co-op. So on top of co-op, you have co-op, this REST interaction between a client and the server, sending get, put, post, and being able to do modification or downloading content. So on top of that, they build a device management system where you can keep alive the device connected using what they call registration, provision the device, and also a REST model for management object, which are standardized. You have a very specific object for describing the device. You need to populate your device data in the device object, and then it's going to be interoperable. I can maybe quickly show you how it's looking in practice. Okay, I'm connected. How is it working? Okay, so this is open source lightweight M2M server. So you can see you have devices registering with the server. And then when you look at the device, you have URL on the device for different objects, and the objects are standardized. For example, the device object is looking like that. You have all the information you need to populate if you want to conform with the standard. For connectivity monitoring, it's a bit the same. You do a read. So as you can see, the read is very slow, well, very slow. It's taking 2 seconds because this is an NB-IoT device. Oh, it's gone. Let me check. Yeah, now it's back. Yeah, you can see the read. It's taking quite a lot of time. It's the time for NB-IoT network to send a packet, then get back the response. So it's not bad. You are in good coverage, but it can be worse than that. Okay, so. Okay, now a bit of feedback from deploying this kind of technology at scale. First, when you really want to use co-op. So using co-op on a Zephyr device is very easy because you have everything ready in the project. You have a co-op client, a co-op server, even lightweight M2M, you have everything ready. But then you don't want to use in every case. You want to use it when you have a constrained network. When I say constrained network is something like cellular and NB-IoT, thread matter, where you have high latency, sometimes high packet loss, or if you want to have some kind of reliability on cellular network where when you are in fringe coverage in bad condition. For example, LTE-M, which is another low power 4G, works well with TCP, but as soon as you are far of the cellular tower and you are in bad condition, TCP is not working anymore, but co-op can work. So that's one of the benefits of co-op. When you want to use lightweight M2M, so lightweight M2M, as I show you, you need to fit into the standard. So it's always a bit complicated. So you probably want to use that if you have a need for interoperability, if you want your device to be able to be managed by different vendors which are supporting the standard, or simply if you need the standard compliance. For example, most of the cellular devices, they have a lightweight M2M client because it's used by the mobile network operator to be able to monitor and reconfigure some capabilities of the device. Or if you have strong security requirements, that could be interesting to reuse lightweight M2M because they have everything ready to provision, certificate, bootstrap the device, put in place key rotation, provisioning certificate on small devices is always a bit complicated. Or for example, if you need to connect to multiple servers and manage access control list between the different servers, that would be interesting to reuse lightweight M2M. But you need to fit in the standard, and it's sometimes a bit complicated. Especially with battery-powered device, low-power devices. I work with a customer which built a very constrained system, a tracker, a package tracker, and the system was really just an antenna, a chipset, and a battery, a small battery, and the system was designed to just last the time of the parcel to go to its destination. They started to use lightweight M2M, but lightweight M2M was not exactly fitting their needs because in lightweight M2M you need to send a packet for register the device, send a packet for sending the telemetry data. So it's 2 packets. So it was consuming more battery than creating something ad hoc with co-op and packaging the 2 together. So they first started with lightweight M2M, and then finally they made the trade-off to give up on the interoperability and move to something proprietary to save some battery. So yeah, it's nice to have interoperability, but for low power devices, it can be a huge constraint. Another thing that is interesting with co-op is you are able to do firmware update with very constrained devices on this kind of constrained networks. But you need to be a bit careful. You cannot just try to send your firmware image from the server to the device because the connection is not great. If the device reboot or the connection break, you will not be able to resume. So maybe you will start from the beginning, draining more and more battery from the device. So what you probably want to do is to first send a URL to the device and let the device download the firmware. When, for example, the device is having battery or the user is not using the device, and let the device deal with it, start downloading, resume if needed, so you can really optimize your system. Another interesting question with the deployment of those devices, those low power devices at scale, is that you often, depends on the business model you have, but for example, if you are building cheap hardware, you sell the hardware, and you don't have a very strong revenues from subscription from the end user. It's difficult to build your system with software as a service that are costing you every month. But also maybe it's also expensive to do it everything yourself. But at the end, since it's a low power device, you will need to optimize a lot of elements, but also the first firmware you will ship will always have some bugs, especially bugs at the lowest level of the communication. And even if you can release a new firmware, the factory, the warehouse will still contain those old firmware with all those old bugs. And you are basically forced to support those bugs for the lifetime of the device, so it could be 10 years. So it could be a bit complicated to do that with proprietary system. Open source gives you a lot of more control on, typically on the server side. Maybe you have one version of the device which behaves strangely. You have a workaround for that, and you will keep the workaround until the device is not supported anymore. So that's why it's interesting to look at open source solution, because you can always fork and maintain your own workaround for managing your mistake from the past, in place of trying to force your software vendor to do it for you. Okay, so to start using co-op. So on Zephyr, it's very simple because you have a co-op client, a co-op server sample. You have also a lightweight M2M client in Zephyr, which are good qualities, are working out of the box. It's not very simple to understand how to use a co-op client and server with DTLS for securing the communication, and also how to use the co-op stack in the client plus server mode, like the device posting element, but also receiving requests from the server. But the lightweight M2M client is doing that. So if you are looking, for example, look in the lightweight M2M client. One of the other interesting constraints, if you want to create a Matter device and you are targeting a certification, you probably want to use whatever thread implementation is provided by your silicon vendor. So most of the time it's OpenThread. OpenThread is containing a co-op client. So you probably want to use this one and not use in parallel of the co-op clients, the other co-op client, which is in Zephyr. and of course they have different APIs, so they are not very easy to switch over. Yeah, and if you are not using Zephyr, if you are using Linux, for example, libcoop is pretty good. It's probably one of the most complete co-op implementation. On the server, you have basically two options. Either you use Java, and in Java you have Eclipse Californium, Open Co-op, which is a bit more recent, I would say, or modern, a bit easier to understand. Eclipse Californium is probably old. It's older, but it's more battle tested, and yeah, and it's a bit more well known. And yeah, if you want to use lightweight M2M, you can start with Eclipse Session, which is pretty complete from a lightweight M2M point of view. Or you use Go. Go, they have a nice co-op library with a DTS implementation. All those libraries are working very well at large scales, are deployed by vendors at large scale. But outside of Java and Go, you don't have a lot of options. The other libraries are not very great, or they don't really exist. That's good. That's it for me. Just to say that Tado is hiring in EU, if you are interested. Yeah, that's it. Thank you. And we have time for questions, if there is questions.
So I was wondering, one of the parts of the presentation that interests me the most is how to get to the client from the server. And you mentioned a few strategies. SMS was one of them, which surprised me quite a bit. I'm wondering, what in constrained environments like that, the two constrained environments that you define, which is battery-powered device but in the home, and battery device but connected via cellular, NB-IoT or LTE-M. What's the as per your understanding, the most common approach to use to get, for example, in the firmware update diagram that you had the initial push from the server to the client of the URL, right? That needs to happen, so that needs to go through the NAT, right?
Yeah.
So what's the most common approach?
The most common approach is to do that is to have the device polling the server to say, hey, I'm here. And then once you have the device connected, then you can do sending the firmware update.
Okay. So not going beyond the threshold of the 30-second threshold or whatever.
Yeah.
Okay.
In practice, you never connect to a device from an IP address or over the internet, maybe locally on the local network, but from the cloud to the device, you never try to reach an IP address. You need to wait for the device to connect. Maybe the device will keep the connection for weeks open for you. And then, you can send a message, so firmware update.
So then on the server side, basically you have, say, a firmware update, you have it queued, and as the next time the device connects, that's when you do the post to the device. Okay, good. Thanks.
And do you have experience with Eclipse Leshan in production environment and production deployments?
Basically I funded the Eclipse Leshan project, and I use Eclipse Leshan for large-scale deployment.
How large?
Millions.
Okay, great, thanks.
Even if it's not out of the box. It's basically my job to help people to scale this kind of open source solution. Because, for example, Leshan, it's coming with a nice sandbox demo you have. Well, it's what I showed you. But it's working on single node. If you want to make that running on multiple nodes at scale with security, it's a bit more complicated. But you can do it. The base lightweight M2M implementation is scalable.
Yeah, I was wondering if you had much experience with like access control and authorization from clients accessing, so for example, like a client, specific clients only being able to access certain firmware binaries or things like that, if you had experience doing that?
Yeah, very small one, like for lightweight M2M, you can have a device connecting to registering, so doing this kind of dense refreshing to two servers. For example, one was just in charge of managing the firmware update. So in the device, it's configured that this firmware update object resource is only accessible by this server. And the rest of the resources, so like the sensor and everything, was configured to be managed by a second server. That means that you need to connect to two servers. You need to maintain two co-op contexts, two DTLS contexts, so it's quite costly on the device, but it works. It's a bit tricky. The standard is not very clear about how to do it, but yeah, you can do it. Thank you. Thanks.
1, 2, 1, 2. Okay. So yeah, hello everyone. I would like to talk about recent addition of ticket speed logs into Zephyr and the initial reasons for all of that. I'm Evgeny Paltsev. I've been working on various pieces of system software for Arc Synopsys architecture and recently for RISC-V architecture as well. All this mostly based on open source projects like Linux, Kernel, Ubuntu, and some other projects. And after some time, I became the maintainer of Arc process architecture in Zephyr TOS. So I spent a significant amount of time making it better for Arc and for others. And thus, I've seen a lot of interesting stuff happening there. And one of them we are going to discuss right now. But first, it's a mandatory cute or funny picture. Here it is. So a few words about the initial reason why we started to dig into this topic and how it's related to Zephyr at all. Some time ago, I was involved into bringing up of our processors with new ArcV3 architecture, which have up to 12 processor cores. And for this system-level testing, we needed something which is SMP capable, which allows us to load system significantly and stress test it with a lot of inter-core communication and all this stuff. One potential candidate here is a Linux kernel, but it's always challenging to debug issues in Linux, especially if you expect what you might have some hardware issues just because you are just bringing up the prototype. And Linux is too huge, it's too complicated to debug, so for the first steps, we wanted to have something simpler than Linux. And actually, Zephyr is a great candidate for this. It has SMP support, which was added in 1.11 kernel version, and it has matured since then. It has POSIX subsystem, which allows to run existing benchmarks and stress tests without or with minimal changes. And we were planning to support Zephyr anyway, so it's not like we are doing some work which we are going to throw away after that. So it's definitely good. And of course, Zephyr is definitely simpler than Linux kernel, at least for now. At the time, our hardware was not ready. So as usual, initially tests were prepared and run in simulation. In our case, we were using Synopsys and Sim for that. It's our simulator. And such things rarely go smoothly in the beginning. Among the other things, we were bumping into the issue that some of our stress tests were failing. And in the situation when you have a lot of in the situation when you have a new process architecture, you have a lot of things which may go wrong. And the issue can be in lots of places. We may have some flaws in SMP implementation for our architecture easily. It could be some SMP-related issue in POSIX subsystem. We've already bumped into several ones, so it could be yet another one. It could be issue with the stress test itself. It could be issue with some of our tools, like in toolchain or in simulator. So lots of things we can blame here. And after a portion of debugging, we found we bumped into lifelog. And it was possible due to the combination of how our simulation works and how Zephyr spin logs are implemented. Obviously, you can just say, oh, it's just the way how our simulation works. Let's just forget about it every time we have something failing on our testing environment. Otherwise, even in best possible scenario, you will end up debugging the stuff on hardware, which would be significantly more challenging. And live logs, it sounds pretty suspicious. Are we the only one who were bumping into such things? And the answer is no. At the same moment, different team from different company was investigated similar issue with Zephyr, but in their case, it was hardware platform with RISC-V. We discussed our findings with them, and in the results, we ended in addition of spin-lock fairness test and addition of alternate spin-lock implementation to Zephyr. But what was the issue root cause after all? To understand that, we firstly need to talk about how spin-locks are implemented in Zephyr. Spin-locks were added to Zephyr with the introduction of SMP support in it. It was done in 1.11 version, and the algorithm itself wasn't really changed since then. Here's the really simplified Zephyr spin-lock code. In real code, we are doing lots of other useful stuff. For example, we check for spin-lock owner to detect situations when we unlock it from unexpected thread or unexpected core. We might check for the time we spent in this lock when it was held. And we are not simply looping, but we call some special spin relax function so we can still process remote function calls from other cores and potentially doing some power saving stuff. So it's actually a bit more complex, but here is bare minimum. So initially, spin-lock was just one atomic variable which was used as a flag. In case of lock function, we turn interrupt off on this core. So the code which is protected by spin-lock won't be rescheduled and preempted by some other code. And after that, we try to set this atomic flag, if it's not yet set. And in a lock function, we do it in the opposite order. We clear the flag, and after that, we turn on interrupts. It's pretty simple, but there is no fairness guarantee at all. For example, if multiple cores trying to pend for spin lock at the same time, there is no guarantee that one specific core will get this spin lock at any time if there is always someone pending. We can lock and unlock it on one core, on other cores, but never get it on some another core. And now a few words about our simulation. Our simulator can simulate multi-core processor, and in that case, it just run and execute blocks of instructions from each core in single simulation thread. So we execute a block of instruction from core 0, after that from core 1, 2, 3, and after that again from core 0, 1, 2, 3, and so on. And simulation is deterministic, as number of instructions in that code block is fixed, and there is no external events or interrupts, as in this case, there were no peripheral in the model we were using, just because we will bring up in the core stuff. We don't need this peripheral stuff. So what was the issue we were bumping into? We had one spin lock which we accessing from multiple cores. It could be some spin lock in our application, like any spin lock, but in the issue we bumped into, it was just a scheduled spin lock from the Zephyr itself. Spin lock was locked and unlocked multiple times when we execute an instruction from one core. But we were always switching to the next core block of instruction when the spin lock was taken. It was just unlucky coincidence, like test was executing stuff in a loop, and the size of this loop interfere with the instruction block size in the simulator itself. So other cores were not able to grab the spin lock at all. It was, and it was scalar spin lock. You can imagine what it affect the system behavior significantly, just because you are trying to get this scalar spin lock and you are not able to grab it at all. And it's not reproduced stably, just because minor code changes may mask this issue. We may like increase or decrease the number of instructions in this loop, so it won't be produced anymore, just because eventually the code would be able to the core would be able to grab this cellular spin lock and test would succeed. So that's why it would be nice to have some test to reproduce it in a stable way. And now we have such test in Zephyr test suite. It's additional test case in a kernel spin lock test. So how this test is done? We just have one spin lock. We grab it, hold it for some time, and release it. And we do it in a loop on all of available cores. We need to hold it for some time just because we need to simulate the situation when multiple cores are pending for this spin lock in a loop. And also, we are collecting per core statistics of number of times spin lock was acquired on this exactly core, just to be able to judge if everything is going OK or not. So we have the test. So let's run it on our simulator on NSIM. We have used, in this example, we have used modified NSIM HS SMP config. We was just bumping number of cores to 4. And where results? As some cores were more lucky, some cores were less lucky, as expected. But what would happen if we run it on real hardware? For that, let's just take this HSDK board, which has 4 ARQV2 cores, and run test on it. Unlike NSIM, unlike our simulator, hardware execute all the stuff in parallel here, just because there's 4 physical cores. So probably we'll get such ideal results when everything is completely fair. Or at least it would be probably close to these ideal results, like this. Well, there's actual results. One core took almost all spin locks, and all other cores were starved. And it's pretty interesting results, but could we expect it from the beginning? So let's have a look on what was happening. Firstly, let's again take a look on how lock function is implemented. We have atomic read modify write CAS primitive. It stands for compare and swap. Sometimes it's also named compare and exchange. So if I use another name, don't be confused with it. It can be implemented. This primitive can be implemented in multiple ways, but it requires some hardware support. For example, some atomic instructions. In this case, we are just using the API provided by Zephyr itself. So we access locked variable in a loop. This locked variable were like internals of a spin lock itself. And we do it from multiple cores simultaneously. And now we need to take a look on our hardware. In our processor, we have private level 1 data cache. So it's quite common design it's quite common to have it so on multiple socks. So it's not something unusual. But in the results, the core which own cache line with the locked variable has more chances to this compare exchange primitive to succeed. So if some core get it once, it's more likely to get spin lock next time. How we can avoid such thing? One possible way is just to use another spin lock algorithm with the fairness guarantee. For example, it could be a ticket spin lock. It's not something new. For example, it was added in Linux kernel a lot of time ago, a lot of years ago. So let's take a look how it's implemented. As it was done previously, we turn interrupts off in lock function and turn them on in unlock function. This part haven't changed at all. In case of ticket spin lock, now we have two atomic variables. One for ticket pointer, another for owner pointer. So in the left part, there is a diagram. So we'll show how multiple cores would be try to take this spin lock and what internal states we will have. This core just marked this, started with number 2 instead of 0, just to not to be confused with owner number. This owner doesn't relate it to CPU ID at all. It's just completely different numbers. So core 2 try to get spin lock. It increment this ticket variable, and it stores local copy of old value of this variable internally. And after that, we try to check the condition. If the owner is same as ticket, if the owner is same as all value of ticket, we can get this spin lock. And in this case, previously, ticket was 0, owner was 0, so core 2 get the spin lock and hold it for some time. After some time, core 3 also want to grab the spin lock. It's same, you go to spin lock function, increment this global ticket, so it now would be 2, and hold the previous ticket value locally, and this previous value would be 1. And now it waits for the condition what owner would be equal to the old ticket value. But we haven't modified owner just because it would be modified in a unlock function which we haven't called from the CPU 2. Now another core try to lock this same spin lock. It would have ticket value 2, and it would be waiting till owner would be equal to 2. So now we have something interesting. Core 2 decided to release this spin lock. It's going to this unlock function and increment this owner value. And now there's potential to threads which can grab this spin lock. In previous spin lock implementation, there was no guarantee if it would be core 3 or core 4, because they are both spinning in one variable, and who was lucky when he gets spin lock. In this case, it has deterministic behavior. So because core 3 is waiting for owner value to be 1, and core 4 is waiting for owner value to be 2. Now we have owner value to be owner value 1, so only core 3 can now take spin lock. So it's take it. After that, it's release it, and we increment this owner to 2, and now core 4 can finally lock its spin lock. After some time, we have this spin lock unlocked. So again, both owner and ticket would be in the same, would have same value, and it's would be incremented after that when someone would try to lock it again, and after some time this value would be wrap around, but there is no issue just because it's totally fine by this algorithm. So now we have ticket spin lock implementation, and let's run our test with ticket spin lock implementation. Firstly, on NSYM. And as we can see, it works nicely. Everything is completely fair. So let's try it on hardware platform on this HDK board. It's also completely fair. According to our tests, it's just nice. So let's run it on something else. For example, on QEMU. We have used modified QEMU Cortex A53 SMP config. We just bump number of cores to 4 to be same number as with other tests. So for now, everything is OK. It's fair. But what would happen if our host is a bit busy? For example, you may feel urge to backup def random into def null, and you want to do it in multiple threads. So here's a simple bash script to do that, which allows us to nicely load the system. So all the cores except 2 would be running with copying of def random into def null. And here's a screenshot from top, so everything is pretty low. So let's run it. Let's rerun test on QEMU. And now we have some issues. Results are not perfect anymore. But what happens here? We have some flow in Spinlock implementation itself. Let's check. We launch QEMU with SMP option. It's SMP CPUs and number of CPUs. So it spawns multiple threads. It will be a thread for each core. So in case of we have 4 cores in Zephyr, we will have 4 threads on the host, which would be representing each core. So in ideal situation, we will have a Zephyr test thread running on some host core. But if we have high load on a host, QEMU threads would be more likely to schedule it out, and it would be happen on different amount of different time moments. So as it was shown here. So if Zephyr thread requests Spinlock, it still get it in proper order. The algorithm itself is okay, but the issue is in another place. Zephyr thread, which would be requesting this Spinlock, may not request it as QEMU thread was not running at all, just because of it was scheduled out on a host. So this thing is obviously cannot be fixed with ticket Spinlock. Yeah. So we improved the situation with Spinlock fairness, at least on some platforms. Do you have any drawbacks with ticket Spinlock? First thing which comes to mind is slowdown. Spinlock is the part of a code which is used often enough. We have more logic in Spinlock function, so have we made some noticeable impact on the system performance? But let's firstly compare how our old and ticket Spinlock implementation was done. So in case of new implementation in Spinlock function, we have +1 atomic get Zephyr primitive, which would be result in 1 memory read and 2 memory barriers. In case of Zephyr, it would be full memory barriers. And in case of KSP unlock, it would be atomic read modify write instead of regular write. Number of barriers would be same just because we are replacing one atomic primitive with another. So it doesn't seem to be really big change. And in terms of how we access the global variable, there's also no real difference. In both implementation, we just spin against global atomic variable, and we are trying to do read modified write access from the loop, from the Spinlock loop. But in real system, it may have some impact depending on the architecture, because with atomic implementation and barrier stuff would be significantly different impact on different architectures. So in case of Arc, we don't have something serious. But there is another thing in this alternative Spinlock implementation which may concern us. There are 2 independent atomic variables now, and is there a chance that they may unsynchronize on some point? Everything would be fine if we just have a lock and unlock function. But we also have a k-spin try-lock function, which try to lock Spinlock if it is available and do not spin if it is not available. And it has tiny window where we may have potential issues. The window is between atomic get and atomic compare and swap primitive. It was marked with this arrow. It's just several assembler instructions where we need to atomic variable to wrap around to have some issues. So what we may do wrong while executing these several assembler instructions? For example, we may try to call lock function with a huge amount of times, with almost uint 32 max value plus something. But as we have lock function blocking, it would require us to have this huge amount of number of cores in the system. So obviously it's not the case, especially in case of Zephyr. Another thing we may lock another option is to grab and release spin lock with, again, huge amount of time from other cores. And after that, to lock it again. If we can do that, we can close the wraparound. But it needs to be done while we executing just several assembler instructions in the context with locked interrupts. So we cannot jump to interrupt, we cannot reschedule. So it's not really possible for our Arc Zephyr port. To meet such conditions, we need CPU core just to hang, which would be much problematic issue if we just have CPU cores hanging. So we've talked about why it won't happen, but let's talk about why it may happen. Potentially, we may run Zephyr on top of some other software. For example, in case of RISC-V, it could be machine mode software if we implemented RISC-V Zephyr port, which would be running in the supervisor mode and not in machine mode like it's done right now. Or we may run Zephyr in virtualization on top of some hypervisor. So now we can imagine some specific use cases which don't require our hardware to be broken to bump into this issue we were talking about previously, about wraparound. So how we can fix that? We may, actually there's multiple possibilities. We can use double atomic instructions to access both variables simultaneously, so it will be just one atomic access. But we don't have such API in Zephyr, and most likely not all the architectures which support SMP in Zephyr has such instructions in hardware. Another option would be to store ticket and owner in halves of one atomic variable. So it would be 16-bit for one for the ticket and 60-bit for the owner. It would be easier, however, we won't be able to use existing atomic increment primitives. We need to implement something on which is based on this compare and swap primitive. So it's definitely possible, but for now it's not yet implemented in Zephyr. So we've discussed ticket spin locks, their advantages and drawbacks. They are available in recent releases. However, they are marked as experimental feature, so it's not enabled by default. So you can use them wisely, and if you have any questions about it, we have some time to ask.
Wait. Yeah, good.
Yeah, so obviously the intent of the experimental feature is that it will mature over time. I don't know if it's turned on or maybe I got too far from the transmitter. The intent of the experimental feature obviously is going to mature over time, and that eventually will turn it off. It's been a while. It sounds like you've got it running on hardware reliably, like you're running the full Zephyr test suite, and in that on that? Yeah. Mm-hmm. Right. Right. Yeah. And so I guess my input would just be, I mean, I think it's time if you guys are willing to say, hey, you know, we've got this suite and it's been running on this platform in our rig or whatever, you know, the intent was always that it be turned off and that we start using this more broadly, and then we would move it to like this or that, you know, emulation platform would be running it all the time. And
well, actually, we already have it enabled for our platforms, and we have it enabled for one of the QEMU RISC-V platform. So it would be tested in the Zephyr upstream CI. And generally, it would be a good idea to have it enabled for other platforms. But again, we need to be careful just because there are some potential issues with it implementation if we are running in some virtualization.
Right. Yeah. Exactly. We wouldn't move away from a default spin lock for a while. But I mean, again, the next step after experimental is, you know, an available option. Yeah.
Probably as we are currently doing a lot of stuff with RISC-V as well. At some time, we are going to implement this S mode port of RISC-V in Zephyr, and for that, it would be probably one point in checklist to have this spin lock implementation updated so we won't have this potential issue at all. Just because there are already implementation in some other projects after we found it, so we can use it as well.
Sounds good. And the other question was going to be, are you aware of any progress actually localizing the original live lock that was reported? I'm just interested personally. Obviously, I was a big thorn in this, you know, saying that like, look, I mean, you know, the scheduler lock just doesn't have that. The, you know, critical sections are all small. I can't see any circumstance where you would then, you know, get stuck in a dueling lock where one party was unable to progress. I don't know if there's
yeah, actually, I've mentioned about it, and yeah, let's just open the proper slide. So yeah, the initial live lock issue was due to how our it's not the thing I was showing.
Oh, it was purely the simulator thing. Yeah. Okay. So
yeah. Okay.
But the number of blocks that then determinizes the order in which the locks are taken. Okay. All right. All right.
Yeah, it's a pure simulation. It's just because we are not doing it in parallel. We are doing just it by bunching instruction, and as it was deterministic, if we get this situation, what we are always graph the lock, and after that simulation would be taking a bunch of instructions from another core. The other core would be seen as this spin lock is always taken.
Okay.
So it was mostly due to how our simulator works.
That's all I got. Anybody else?
That's actually a question on YouTube, so I'm gonna read it. It's from Wilfried. And Wilfried is asking, some platforms don't support cross-core atomic operations like the RP2040. Would Ticket spin lock be portable to such platform requiring SoC-specific primitives, for example, using hardware spin lock?
That's a good question, and probably to answer that, I need to check how the hardware spin lock are implemented, but generally, even the original spin lock implementation required to have these atomic read, modify, write variables. So I'm not sure if and how this original spin lock was implemented for them, but if they use some other things instead of this read, modify, write atomic instruction, probably it could be a way somehow to implement it, but I need to check this hardware specific firstly.
Yeah,
it's really have a lot of influence on how we can or cannot implement it.
Right, we had a driver submitted a while back that was a hardware spin lock, and in that case, the hardware actually managed the fairness management. That you didn't need a ticket spin lock because the operations at the hardware level were like lock and unlock, and it would handle that all for you.
Yeah, that's true, but
different hardware, yeah.
Yeah, that's true, but there's no information if the hardware maintain this fairness or not, and if it's not, then probably they want somehow to work around it.
So I think there is actually another question to that person. So I don't really understand if true SMP system could be implemented with such a memory approach, because if there is no coherency between cores, so how that could be even possible, and that question then makes no sense, because all of what we had in that presentation, it is related to SMP system only, because in AMP system there will be another way of synchronization things, and on single core system there is no problem at all. So it is kind of a question without or taken out of the context. So yeah, I don't know. Typically those kind of things which we are seeing here, they are implemented on top of the cache coherency protocols. And so if you don't have cache coherency, there is no such kind of primitive at all.
There can be, like extensive, for example, is a cache incoherent architecture. It actually does have an atomic primitive, it just goes through the cache. So different hardware is different.
Yeah, possibly.
Yeah, I've seen these hacks for Extensa, but I never actually investigated how it's done for them, just because luckily we don't have such a requirement.
All right, we still have time for a few more questions, if there are any. Not on YouTube, not in the room. All right, thank you.
Thank you for joining.
Okay. Can you guys hear me? Good? Yep. So let's get started. Last presentation of the day. Thank you everyone for being here. I will be talking about not as technical as the previous presentation, going into spin locks and SMP and so on, yeah. But there are like a few interesting things that I will be showing. So it's not only, general graphs, etc. It's going to go a little bit technical, yeah. Basically, we have been collecting data and tracking data in Zephyr for a while, actually since the project has started. I mean, when it was started 8 years ago, the first thing we would start, counting, looking at commits and looking how many boards were added last month. Started with 8, or like a handful, actually, a handful of boards. There were, obviously, we also had a few drivers, and that started growing as well. So these are like the type of things we were tracking. And that was mostly, to see if we are like healthy, if things are going well. And 8 years later, which is basically this year or today, we basically established like constant growth in all of these areas, like commits, like number of boards, like drivers, hardware supported, and or architecture supported, and so on. And recently, or in the last few years, we started also tracking all kinds of things that go beyond the obvious metrics, like commits and number of boards. We started looking at things like, metrics that are related to project health, performance metrics, KPIs, key performance indicators, talking about performance here, footprint, and so on. And other metrics that in many ways keep us honest toward our community, yeah? Trying to track, like, how long it takes for something to get merged, the review times, how long does it take for an issue, to get resolved, and so on. So all kinds of things that helped us also improve, our performance as an open source project, but also keeping like to the promise with which the project has started, which included something like, constrained devices and minimal footprint and running on different architectures and so on. So when tracking metrics and you can go really wild in the things that you can show and display. So you can go, about issues, about how many forks and how many stars you have on GitHub, how many downloads. Although, downloads doesn't really apply in our case. The documentation and how it evolves, how many organizations or users are using Zephyr, number of contributors, et cetera, right? There are so many metrics and so many key items that you would use to track an open source project and see if you are healthy. I will focus a little bit on the technical side, not on the social side of things. And I will be showing, have a few use cases or a few things that we are tracking, show basically how we have been doing over time, and also, how we are using this data and how we are reacting to this data. So the things that over time we have identified is that obviously there is constant growth. I talked about that in the community. The code base itself and hardware support, and also the use cases of Zephyr in terms of like where it is being used, the different features that it supports, and so on. We're also using some of the metrics that I will be showing. You will also see that it is, easy to say that, or it is fair to say that we have a stable core of the OS. There are a lot of fluctuations here and there, but things that are manageable and things that are usually expected And it's not always going in the negative side. We actually have very good improvements over time. I will show a few of them. Some of them would be familiar because they would correlate like to key events in the tree. And it's very easy to identify and see and understand also why these things are happening. So I mean, metrics are not always there to show you that you are doing something wrong. They actually show you sometimes that, hey, you are on the good path and you are doing something right. So let's start with a few case studies and a few examples of things that we have been, of data that we have been tracking. So the first one is a little bit social, but it's a very, important metric in my opinion, and something that, depending where you are looking, you get different numbers, right? I mean, it's a matter of definition at the end of the day. So if you look like, for example, on GitHub, you will see that we have like 2,000, I mean, that's what, like one of the numbers you will see, 2,039 contributors, according to GitHub. And that number basically means that since the project was started based on the code base and how many commits you have there and who has committed, we have over 2,000 contributors. Obviously, that does not mean that at any given time we have 2,000 contributors, but over the life of the project, over 2,000 people actually worked on the project, contributed in one way or another. In this case, it's going to be a commit. Somebody committed something. If you look at Git, it's a little bit more because the project goes actually beyond GitHub and before GitHub, and there are probably a lot of commits in the tree for users who actually don't have an account on GitHub or there is now, I mean, GitHub can't find who that is, etc. So it's a little bit more, and I mean, if you attended my session last year, and some of you probably did, I mean, the history of our project goes beyond or before it was posted to GitHub, a few years before and maybe more years before it actually was planned to go and become Zephyr. So this is according to GitHub. If you look at the Linux Foundation, I have actually all the links for some of these dashboards and areas also linked at the end. There is a dashboard like with a lot of metrics from the Linux Foundation that tracks various projects managed by the Linux Foundation. And Zephyr is one of them. And there, basically, the number of contributors is tracked as over 6,000. And that's due to the fact that contributors are considered anybody who has touched or did anything on GitHub. So you can actually be submitting an issue or editing a wiki probably or doing whatever. You are considered a contributor, which is fair, right? I mean, that's where like contributors sometimes the terminology is a little bit confusing. So I think that contributor, anybody, you don't have to be committing code. You might actually be just participating in meetings and discussions, and you are a contributor. That's great. So it's not always about code. So this is just shows like the numbers, and something interesting that you can extract from Git and other sources is also like trying to see the growth over time. So here, basically looking at how many contributors are active each month since the project has started. So obviously that does not show the 2,000 number. This is, I mean, if you look at a per month basis, first we have growth or constant growth, which is really great. And if you look at like the last month, we have like in the last month over 200 people active working on the project, which is also a good number. And that actually correlates and it corresponds also to the number of commits going into the tree. So it's nice to see that these two graphs actually align. Which, I mean, then you'll start thinking, who are these 200 people, and are they, is that the same number of people going, and just more people are joining the same number or a core team, or does that change in a dramatic way over time, etc. And that's where I wanted to look and see and understand, because it's very important that when you run a project like that, to see what's happening, who's actually running the project, and who's loyal to the project, and who sticks around, right? So if you look at this graph, you will see, for example, that we have like almost 100 contributors who worked 2 or more years on the project. We have like 50 of them who have been working on a project more than 3 years. So, and the blue section here which is the majority of contributors, are people who actually worked less than a year on the project. So that shows that there's a core, contributor block, and there are a lot of people who come and go all the time. And that actually can also be seen in terms of commits. So basically, we see that, we have the majority, like 1,800 or something like that, with 1 to 10 commits. And then a very small number, like with commits that go into the thousands. And probably, if you look around, some of the top, committers in the project, you would find them in this conference usually, yeah, because they have been there for a while and they are very involved and so on, yeah. So basically, it shows that the way the project is done, we always have new faces, we always have new contributors, also new ideas and new code coming in, and it's not like the same core dictating or managing the project in a way that is not subject to change and so on. So there are new faces, new ideas all the time, which is really great. With that, I will jump to something else, which, many of you probably haven't seen before, because although it was available, or we have been looking at and working on for a while, it was not public in terms of, like, it was not published for everyone to see. And that's performance tracking. In this case, over 1 year. That's something we did like a little bit retroactively. This is now available. I will show the link later. This, obviously you need to understand what that is. We have a test or a benchmark in the Zephyr tree called latency measure, which does actually go and test like key metrics like context switching, semaphore taking and giving, with mutex, heap, memory allocation, and so on and so on. And there are also different variants of this benchmark. So this one I'm showing here is like the most basic configuration. You can enable user space, then you can see also numbers with regard to context switching between user and kernel threads and so on. Yeah. And obviously, immediately you will notice that there are like big jumps in the graph there. In this case, these numbers are going down, yeah, which is not bad, yeah. But you also see a lot of things happening there as well. Okay, for example, this is actually very recent, early March. And I saw that and said, oh, okay, that's suspicious. What's going on here? And one thing that you can do here is go and bisect and see what happened here. Is it justified? Is it my script? And so on. And I bisected that, and that's a commit that introduced that. That was me, yeah? So I was not happy about that. And I had to go and look and see what exactly happened there. And if you look at the commit message, this was no functional change. I was just moving things around, trying to clean up the tree. And talking with Peter, one of the kernel maintainers, and looking also at the change itself, at the commit, I immediately noticed that, I mean, okay, I moved, I mean, we had a lot of functions, a lot of functionality, or a lot of the implementation in one single file in the kernel. This is the scheduler. And a lot of things were, I mean, basically declared static inline. And when you start moving things around, you would assume the compiler would take care of everything, etc., but that's not the case. That, by the way, the bump or the change is actually very minimal. We are talking about 500 nanoseconds or something like that. And by the way, this is using chemo. Yeah, so this is using chemo. I'm not even trying to use hardware here. And we established, or by running the data on all the emulators, some emulators are a little bit, you know, they go up and down in a crazy way. But some of them are actually really stable, chemo and other simulators. And I'm not interested in saying here, or seeing like speeds, or like trying to meet a criteria, or like certain numbers. I just want these simulators to be stable. So if I run them on a code from 1 year ago, and now, I should see basically the same trends, and not things going up and down like crazy. And that this is like a RISC-V chemo, I think. And you can see there. And by the way, so I actually went and moved things around a little, put like some of the functions, which are utility functions, in a header, moved it and submitted a pull request. Interestingly, my fix for this problem improved the performance and brought the numbers, or made it better than before this commit. So something, actually, at the end, a net gain of 500 nanoseconds after the fix here, which is really great. So this is one. There are this is also part of the dashboard. We are using Elasticsearch, and this shows you the difference that we have. Basically I did it like on a weekly basis. So from week to week, like every week since last year, I would go and run the benchmarks. And you will see like this shows the difference from the last value. So it would immediately show you, for example, where certain changes have happened. And over the last year, you will see that there are fluctuations, but these are like very minimal. We are talking about a few nanoseconds here and there. This is like, you know, you add like one line of code probably in some function in the kernel, you know, to fix a bug or to improve something, and that would show up here. Yeah, this is how sensitive it is. However, we also noticed like major changes there. This one can be contributed to this guy here. Yeah, this is the drop, which is actually a positive thing. This is when we move to Picolipsy, yeah? And this is the memory allocation. I think the heap something, I don't remember right now, but this actually is one of them. And if you remember, we also had this, we have seen the same thing in the footprint, yeah? I will be showing that. But this is like one of the things that came out of the Picolipsy, making Picolipsy the default, yeah? And there is a few others that I will be talking about as well. So here, that's basically one of the tests that we have. It's the kernel abort kernel from kernel. And you will see that this is like a step function. One change happened in November, and the other one was in early March. I bisected. The first change was introduced by Peter Metzes, one of the kernel maintainers. And I looked at the change. I mean, this was like really a functional change, a bug fix mostly. I mean, adding and moving things around. So a change in the metric would have been expected. And I don't see that as a regression in this case. Yeah, I mean, looking at like all of the code that was added, you know, the branching, the conditionals, etc., that is something that is really expected. The other one is actually the same commit that I was talking about earlier. Yeah. So actually, with my fix, this actually will go a little bit down as well. So I mean, the net change there is something minimal and acceptable. Yeah. Now going back to this is performance, and I'm just showing like one aspect of that. If you look at footprint, which we have been tracking actually for longer, and it's also public and available on stats.zephyrproject.org. Something that we want to move to the same infrastructure we use right now using Elasticsearch and Kibana. And you will see, actually, it's over time. And by the way, this is on Freedom Board, like one of our earliest boards that we have in the tree. We have a few applications, like here, the footprints. This is a footprint application, and here it's using user space. So different configuration to see basically what's going on. And over the years, since like almost 2 years, it's actually not bad. It's going down like on a constant basis. Yeah? And a major drop happened when we introduced Picolipsy as well. Yeah? So it has major impact on the footprint in a positive way. But we keep seeing like drops whenever we optimize or overhaul the code and so on. So it is definitely going in the right direction. This is not an exact science after all. I mean, sometimes, you know, a K-config is dropped. Sometimes you might be actually dropping like one feature here and there. So it's not always the code being optimized, the same code. Sometimes things go away, but at least this will give you a trend. And the way it is done, so it's not like just like an image number. It actually goes by the, you know, by the components that you have in the binary. So you have the kernel, you have, you know, the subsystems and so on. Actually, and now we are looking into going deeper because some of the subsystems like Bluetooth or networking are so big, and the maintainers of these areas want to zoom in basically and look at their own subsystem so they can optimize at the subsystem level. So we are working on adding additional layers so people can see exactly where, for example, in the Bluetooth stack, they can improve or how they can track the footprint there. Another one, basically also related, coming from the footprint. This is without user space. And the drop at the end there, I think that was last year in August or something like that. That's also related to the Picolipsy change. Yeah? If I see that correctly, yeah. Okay, so this is like footprint and performance. So all of this is available online. It's actually being tracked and updated on a daily basis. The benchmarks, it is online, and I need just to submit like this. We need to submit the CI change to start tracking that on constant basis. And now this is all great, and it is, you know, very useful. However, there are other things. I'm trying to move to the next slide. Did I freeze or what? Okay. Use slideshow. Okay. Let me go back. Okay. So beside the social stuff and number of commits and contributors and the performance and footprint and so on, we also try to track things that relate to our day-to-day work and operation of the project. And one thing that we started late last year, earlier this year, is tracking like the merge criteria, making sure that we keep, I mean, we keep ourselves honest toward the community and toward, you know, our colleagues in the project, and try to be consistent in how you know, pull requests and changes are processed and dealt with. So this is something like part of our guidelines and documentation, is that We have some criteria defined for merging a pull request. So for example, needs to have a minimum of 2 approvals, including an approval by the designated assignee. That means that the maintainer of the area that is being changed. We have the 4I principle on the organization level. That means if the submitter, the reviewers, the assignee are from the same company or organization, the merger needs to be from a different organization. Yeah? And that's just to make sure that things are played in a fair way and things are not rushed into the tree by one organization. And then a minimum review of period of 2 business days, 4 hours for trivial changes. And hotfixes can always be merged. So I mean, this is something that at least most of these things can be tracked and can be accounted for using scripting and so on. The 4 I's principle, this is something that we are still working on, so we are monitoring that manually. But based on this criteria, we actually provided this here, provided by Fabio from Google. It's like a merge list to make it easy for people who own the merge rights to actually go and look at what is ready to be merged. And that actually has been working really well. Almost we have been using that for 2-3 months. And it had helped a lot with how we deal with pull requests and how we merge things. And we got a lot of feedback last year in the developer survey and also in the conference ZDS in Prague. And since then, we really got a lot of, we made a lot of progress, and a lot of people are happy with how is it working. Just to show you an example, this is a dashboard we created to track basically also any pull request that is merged, basically tracking who merged that, who was the submitter, and so on. And it has helped us identifying trends. And and with when you start using also the merge queue or the merge list, everything is transparent. People can see exactly what's happening over time and who is leading the charts in terms of merges and who's leading the charts in terms of submitting pull requests and so on. So it gives us like an idea and see exactly how things are going. But it also shows us if we are violating our own rules. And this is the example here. So we have like 2 bar charts. And this is, I think, over the first one is like 2003. It shows you like assignee approved. No is almost 15%, which is not really great because that means we have merged something that was not approved by a certain assignee. It's not always bad because sometimes there are exceptions, but 15%, that's way too much. That means we are doing something wrong. Either things are being assigned to the wrong people or assignees or maintainers are not being responsive and so on and so on. The other pie chart is showing, pull requests that have been merged with giving enough time, for people to review. 60% yes, and no, almost 40%. That's not really great because that means we are rushing things in, sometimes not giving people enough time to review. Yeah. So this is 2023. Yeah. If you look at 2024, and we started like I think in February to start enforce and people getting accustomed to the dashboards and then your script and the merge list, that number actually went down. Yeah. So at least for the assignee approved, you will see that NA means there was no need for this, or there was no assignee because this area doesn't have a maintainer and so on. Yeah. But the number in red here, that's basically a major improvement from 2023. Similar thing with the review time. So that means that we went down from almost 40% to 10%, which is really great. That means we have enough time we giving people enough time to review things. If you look at like just last month, that's even better, right? So we have been like really doing well on both fronts, and I would assume like even like these, you know, the things that did not go or did not follow the criteria probably were just exceptions for whatever reason. I mean, our scripts, after all, are not that perfect, and sometimes you have the wrong label or the wrong assignee and stuff like that. So we have been doing really well. Just going, I mean, on other dashboards and other data that we use is like we have the code coverage, something that we run also on a constant basis. Every time we push the tree, I mean, using at least the tools that we have and the capabilities that we have, we are able to extract coverage information for basic functionality. Yeah? So it's not every feature that we have in the tree, anything that we can run in CI. We have our own dashboards for tracking bugs and issues, and something that we use on a daily basis, basically, or on a weekly basis when we do the triaging, so on how many high priority, medium priority bugs, and so on. And we also have static coding analysis charts and data that comes from Coverity in this case, and does not really, it's not something that we produce, but we at least we do the scanning, submit to Coverity, at least the open source side of Coverity. And we get like, because we have been doing that for a while, we can get like some data about, you know, the type of issues that are found in Coverity and so on. So that's really great as well. So there are many places where we actually can collect data. But that's not great because this is like all over the place. And we are trying basically to consolidate and gather all the data in one dashboard or one place. Ideally, this would be Kibana Zephyrproject.io, which is our Elasticsearch instance. We want also to try and create a feedback loop so that, like, if there are anomalies and if there are major drops in performance, or even if there are positive how do you call it, improvements, yeah, then we want to know this. It shouldn't be that, you know, somebody should be watching these things. So we need to figure out how to get notified when something happens so we can, you know, respond immediately. We want also to identify issues as early as possible. So right now we do it on the tree, on the checked in code. We want to have certain checks run on pull requests. So if somebody increases the footprint, they should know about it. Or if their change decreases the performance of the kernel, context switching, or other metrics and so on, they need to see that so that we don't merge the code and fix it later. We can react to it as soon as possible. And we want to obviously to add more metrics using hardware, because a lot of the things that we have depend like on simulators and stuff like that. And it's very important that we also see how things work in real life. So we are looking like at using, for example, tracking timer accuracy using also like logic analyzers and other external tooling. We want to go further and look at various subsystems, whether it's peripherals, whether it's networking, Bluetooth, and so on. Yeah. So we definitely want to increase that and try to have everything in one place, which would definitely improve the overall quality of the project. So key takeaways here is that tracking helps with enforcement of project principles and guidelines. Yeah, this is like in terms of footprint, in terms of the merge time, and so on and so on. Yeah, visualization of project activity provides an early and transparent alarm system available to all stakeholders. It is key. I mean, a lot of these charts, sometimes you create them, you look at them yourself. It's fun and so on, but I think that the most important thing is whatever we do here is available to everyone exactly the same way and exactly using the same infrastructure so that more people can first contribute with additional metrics, but also so we can have people analyze and look at the data and come up with solution, whether it's technical metrics or even like things that are related to how the project operates. Yeah. These are the resources, GitHub Insights. All of you are familiar with that. LFX Insights, it's insights.lfx.linuxfoundation.org. And I will actually show that briefly because it's actually really nice. I hope I can do this in the last few minutes. So here, this is, okay, so this is, and it's, oh, okay, I can look here. That's good. Let me start with this. So this is the metric stuff. As you can see, you can select the platform that you want to choose. Some of them are really flaky in terms of you can have multiple platforms, then it looks really weird, yeah, because they are on a completely different scale, yeah. So usually you would actually want to go and select one. And you can, this is the difference here. And you can go and look at the metrics one by one here, yeah? So that's something that you definitely need to go drill down and play with the numbers and so on. But I think this guy here helps a lot identify when major changes have happened. And you can actually also select which metric you want to show. So here, like, oh, I'm interested in FIFO get blocking kernel to kernel. You can do that. And you can see exactly what's going on here. So this is one. This is the dashboard that we use to show that to track the merge criteria. This is like the last 30 days. Shows you exactly who's active, who's merging, who's submitting, top submitters, top reviewers, and you can actually go and and select also like a name, in this case here myself, and see basically what this guy is going and who's merging the pull request and so on. It is really provides some transparency on how we are dealing with our community and code changes. So that's that. This one just shows like the bugs, high priority, medium priority, etc. Goes back to 2019. No surprises here. I mean, the numbers go up and then go down. I mean, this is when we triage them probably, and it's like a constant curve if you want, yeah. This one is the footprint. You can go in and select which application. So we have a lot of Bluetooth application here. We also have a lot of example platforms because different architectures behave differently. You can also, beside Flash, you can also look at RAM. So RAM actually doesn't change much. This is like stack and stuff like this. So it's steady. A lot of the changes usually and fluctuations happen on the footprint side. Sorry, on the Flash side. Here, this is Coverity, yeah. But that one, LFX Insights, that's actually really interesting because you have to be careful when you look at the data and read exactly what each metrics means. And that's actually very well explained in the pop-up here. But it actually goes into a lot of things related to open source projects. So it goes into issues, pull requests, forks, stars, etc. And it's really nice sometimes to see where are you standing and if you are doing well and so on, or if your company is contributing enough and so on. Yeah. So that's really great resource as well. Take a look at that and yeah, play with this. There's a lot of data. Yeah. With this, thank you everyone, and if you have any questions, I'll be happy to answer them. Wow, right on time. That's good.
Yeah, I've tried to go to these provided links like stats zephyrproject.org and Kibana zephyrprojects.io. And in my case, I don't see anything statistic. Like in case of Grafana, it's just default Grafana page without anything. In case of Kibana, I try to go as an unlocked user, and again, I see no data at all. Do I need to be in some specific group?
No, it should be anonymous. We can take a look at that after that. Maybe it doesn't work on your mobile or something like that. But
yeah, it could
we'll figure
be,
it out. Yeah.
Okay.
They are anonymous, yeah, so it should be fine.
if I develop application or drivers out of tree, would it be possible to replicate some of these dashboards, specifically around code health, locally or in an environment?
Yeah. So for example, the benchmark stuff is something that you can run in the tree on any board, on any driver, on any hardware. Yeah. So it's actually, this is code that is available in the tree. Same thing with the footprint analysis. All of this data is based on scripts and tools that we have in the tree already. We just collect it in a certain way and push it, to these. Obviously, if you want to visualize and so on, you can do that also using Excel or whatever, right? I mean, you don't need to use these tools. Yeah.
Okay. Thank you.
You didn't mention about test results, about tests that can be executed on board farms. Are there any plans to make this public? Or?
Well, I mean, the data is there. Yeah. So, I mean, if you go there, but that's like a testing, where is it here? That's, I didn't look there for a while, so excuse me if that, no, actually it's working well. Yeah. So last 7 days. So if anything that we push into Zephyr, when we run the test, we actually publish the results, all of the chemo results and so on, yeah? So all of that is also being published. It's also public. We want, as you mentioned, to actually establish something like this also, like for hardware farms, so like different users and vendors can push the actual results of tests running on their hardware into one common place. And that's something that is in the works right now. Right now, all of the data that you see here, which you can access anonymously, is based on chemo, yeah? And that just gives us an idea of, how many bushes and how many architectures and how many platforms, how many tests, which areas are covered most. You will see here, like the kernel, libraries, logging, etc. But you will also see that certain areas are not really covered. And I'm talking here about running tests that are actually run and not just built like on platforms. So a lot of coverage we are getting using native POSIX and chemo. And a lot of features that are not testable in emulators will not show up here. Yeah, and that's really bad. And hopefully this will change in the future once we start running on hardware. Yeah.
So what I'd like to see a little bit more like statistical porn, specifically about, for example, tests which we run in upstream CI, to see how we are first growing number of tests which we execute and maybe different configurations, because for me it's interesting how it could be sold to somebody saying, okay, so you may measure coverage in different ways, but if we are growing the amount of tests and we growing the amount of platforms and architectures, so then you also see what amount of background work is being done actually. So for each PR, how many things you check and test and everything. So that is one thing.
That's exactly what you see here. Yeah, I mean, like 2,600 test suites, 20,000 test cases. Platforms 1,000. 1,000. By the way, this is because of the hardware model v2, because now we have like old platforms that have new names, and in the database they appear a new. Okay, so this is.
So can you plot these platforms on a graph to see how it evolves with time?
Yeah. That, I mean, there are different ways to display this. By the way, here, for example, you see like which platforms are executing most of the tests, and Native Simulator right now is leading the pack. Yeah. Chemo x86 as well, because that's where we do like user space testing. Unfortunately, I mean, that does not appear here, but there are, I mean, it would be really great, like if we can also, for example, from Synopsys, we could run InSim somewhere, right? I mean, we do that. I have access to that. I mean, there is ways to start publishing this data here as well, because by the way, in the performance, I had InSim as well. Yeah, so that's, which I liked really much because it's very predictable, very deterministic. Yeah, which you can use as as a reference. But I didn't choose to use it because it changed names, in the last month, so that would skew the graphs. Anyways, yeah.
Okay, thank you.
Thank you. Any other questions?
There may be last question.
Okay.
So yeah, great to see basically the compliance with our policies on the merge policies. But what was the impact overall to like merge times?
In terms of?
Yeah, so yeah, like what's happening with our just overall PR merge times? Like, is that,
I mean,
I know that's something that Benjamin's been tracking as well. So
yeah. I mean, it's not like we are deteriorating or it's becoming worse. I mean, I think it was really bad that we were merging too fast. Yeah,
Mm-hmm.
and right now there is at least a checkpoint or like a way to see, okay, this PR is ready to be merged because it was reviewed enough based on our criteria. It was reviewed by the right people. There's the assignee has approved, etc. And you see it in one place, so there is no doubt that, hey, I can merge it or not. Sometimes because people didn't just want to start calculating times and so on, or they were nervous about merging something. Now we have something that would give us like some assurance that, hey, this is good to go. That doesn't mean that you just go and click and merge it. Sometimes you have to go as a release engineer and spend some time and figure out, okay, maybe I need to add another review, or maybe I can't merge it because I am in the same organization and so on. But in general, we are around these like 2 days, 3 days for pull requests that are ready to be merged, which is really great. Yeah. Last question.
Thanks. So you mentioned about like showing these benchmarks, and so I often realize that there's a case that people ask you to, like, let's create me some dashboard because it'd be super interesting, but then in the end, no one is looking at it. And I think that's what you mentioned, like with this benchmark, that you are looking at it and trying to identify the peaks and when it happened. And you also mentioned that you are looking in the ways how to automatize it and basically doing some kind of alerting system. Can you give some insight into it?
Not yet. That's something that we want to have. I still didn't look in a way how to do it. This could be used like these systems, like Elasticsearch or Kibana, but it can also be done in different ways outside. We need to see how it can be done. Yeah, I don't have a solution. Yeah.
Okay, thank you.
Thank you.
Okay, thank you, everyone.